Okay, let's start. Good morning.
Sorry. Thank you all for joining today's IEEE Computational Intelligence Society webinar held as part of IEEE Education Week. IEEE Education Week highlights IEEE's worldwide educational opportunities, from STEM outreach to university programs for professional development through events, webinars like this, courses, and special offers. For more information and other events taking place this week, please visit educationweek.ieee.org. We're grateful to Ying, chair of the CIS webinar committee, for her leadership in organizing this event, and to Parth Gupta for generously sharing his time and expertise with our community. Before we begin, I just want to note a few housekeeping items. Lines will be muted during the presentation. You may enter questions in the chat box at any time. We'll reserve time at the end of the webinar for Q&A, and this session will be recorded and posted online on the CIS website at cis.ieee.org. I'd also like to remind everyone that our next CIS webinar will take place on May 12th. Later in the webinar, I'll drop a registration link for that event in the chat. And then just a reminder, you can stay informed about other upcoming events in CIS on our social media, Facebook, LinkedIn, and Twitter. And with that, I'll turn it over to Ying to introduce our speaker today.
Thanks, Tom. Good morning, good afternoon, good evening, everyone. Welcome to this seminar, this webinar. On behalf of the IEEE CIS Society, it's my pleasure to introduce today's webinar, held in celebration of the IEEE Education Week. I'm Professor Ying, and I will be the chair. Today's webinar topic is about applying machine learning to transaction monitoring. As you know, money laundering accounts for 2 to 5% of global GPT, and the traditional rule-based system generates too many false positives. So how do we move to the proactive risk-based detection? That's what we will explore today. So we are incredibly fortunate to have the world-class expert to get us through this technical landscape. Our speaker is Parth Gupta, Vice President and Applied AI Machine Learning Lead at the JPMorgan Chase, and an active IEEE young professional. Parth will bring deep expertise from his prior leadership roles at American Express and Adobe, and holds advanced degrees from Columbia University and IIT Rocky. His work focuses on building explainable models for credit risk and financial crime. Precisely the skills needed to detect the extremely class imbalance and operational challenges we will hear about today. So please join me in giving a warm welcome to Parth Gupta. Welcome.
Thank you, Professor Ying, for the introduction and giving me this opportunity to present. So as Professor Ying mentioned, that I will be presenting on the topic application of machine learning in transaction monitoring, right? Moving on. So before I begin, I would like to give some disclosures. So the views and opinions expressed in these presentations are mine and do not reflect the policy of my past or present employer. Also, the figures provided in terms of model evaluation are aggregated research benchmarks, and they do not represent the specific production performances. With that, let me begin. So the agenda for today's presentation is first we'll talk about transaction monitoring, right? What it is, why it exists. What is the cost of failure, right? And then we'll look at the key challenges in developing machine learning approaches for this kind of problem. Then after that, we'll go to the model background. We'll discuss how to design model for such problems. And then finally, the model evaluation, like how do we design metrics and calculate the performance of such models, whether it is robust, whether it generalizes well, all those kind of things, right? So that is the agenda for today's presentation. With that, let me start with what is transaction monitoring and why it exists, right? So let's first look at it from the regulation point of view, right? Like regulations like Bank Secrecy Act, Money Laundering Control Act, They impose record keeping and reporting obligations on financial institutions to deter and detect fraud, money laundering, and other unlawful activities. Right? These obligations include requirements to monitor for, investigate, and report any kind of suspicious activity to Financial Crimes Enforcement Network. So FinCEN is basically the main regulatory body that governs it. For the remainder of the slide, when I refer to suspicious activity, I will be referring to money laundering instead of the fraud. So we are excluding fraud from the scope of the discussion, but it will be focused mostly on money laundering, right? Now that we have understood the reporting obligations, like financial institutions have a compliance program called transaction monitoring, which is designed to identify instances of potentially suspicious activity involving its products and services globally, right? So after looking at the regulation piece of it, right, let's understand what money laundering process is and at a high level how it works, right? So the first of all, we need to get some illicit money, right? And this is basically dirty money or cash from some criminal activity, right? So there are three stages of how to clean the money, right? So the first one is placement. So what you do is you deposit the money into the bank in small amounts so that it is there. Then the second stage is layering. What you do is you move the funds across the worlds so that the origin is obscured, right? And finally, the integration. You try to merge all these small amounts together and try to do purchases for luxurious items such as cars, jewelry, and real estate, right? So now that we have understood what the regulations is and what the money laundering process is, now let's understand how transaction monitoring works, right? So transaction monitoring program is a rule-based system that flags potentially suspicious behavior. So let's look at the flowchart below, right? Just to understand how it works, right? So for example, whenever a transaction is done, it is analyzed by a rule-based system. And based on the threshold, that transaction could either be triggered or it is not triggered, right? So if it's not triggered, then no action is required. However, once it is triggered, it goes through a human review, and these are special analysts who have the expertise of reviewing such cases. After that review, if suspicious activity is found, they need to actually draft a report and file it with the regulators like FinCEN. And if no suspicious activity is found, they still have to write a report, but they don't have to file it with the regulators. Now, why it is challenging, right? Because of the volume and frequency of these alerts, right? Like for example, in a day, you can have multiple alerts, right? However, there is a strict deadline to review each of the alerts, right? So you have to complete it within some deadline from the day of generation. And what it is found is that about 95% of these alerts are false positive, right? Essentially, the reviewer is working on a lot of low priority cases that are not suspicious activity, but just because they were triggered, they have to review it, which is increasing the workload of the human reviewer. So this is how the transaction monitoring process generally works. Uh, Now let's look at the cost of failure, right? Like I will talk about some of the recent penalties and fines and what were some points from the regulatory findings. So in late 2024, TD Bank was fined $1.3 billion. That's a lot of money, right? And it was fined by FinCEN. And one of the point that was highlighted in the regulatory finding was from 2017 to 2021, TD Bank facilitated over $400 million in transactions from an individual who pled to money laundering in 2022, but their system was unable to detect it, right? So this is one of the key points that they mentioned in their regulatory finding. However, the total fine was almost $3.1 billion because there are other regulators also involved, but $1.3 billion was just from FinCEN. Another example is for Capital One. In 2021, they were fined $390 million. And one of the reasons was because Capital One admitted that they willfully failed to file thousands of suspicious activity reports to the regulators, right? So it's a regulatory requirement that you have to actually file this SARS with the regulators. Otherwise, there are going to be penalties, right? I'm going to talk about one old example in 2012. HSBC was fined $1.92 billion, right? That was like the biggest fine at that time. And one of the points was that HSBC did not have sufficient staff to review the alerts that was generated from bank's monitoring process, right? So essentially stating that there is a need of either like more staff, or they need to review sufficiently all the alerts that are generated, right? However, like apart from penalties, right, like institutions also face lasting reputational damage and loss of customer trust. Like these are also like equally important risk for not complying with EML regulations, right? So now that we have understood like what is the cost of failure, let's talk about the key challenges first, right? Like for example, if we were to approach a modeling solution for such a problem, what would be the challenge, right? So the first one is so there are four key types of challenges. The first one is rule-based limitation. So the first aspect is like all triggered alerts are treated equally regardless of risk. Once you are triggered, it does not differentiate between a low risk alert or a high risk alert, right? The second one is a rule has static threshold, right? Which requires frequent manual updates. And it's a very time consuming process because once you set a threshold, you do not observe any review for population that lies below the threshold, but you would start seeing the reviews above that threshold. So that's also a very challenging problem on how do you set those thresholds and how do you sufficiently test that that threshold is good enough. The second aspect is evolving patterns, right? So both suspicious activity behavior and human review evolves over time. And this is more like a concept drift that happens both in the review side as well as in the suspicious activity side. The third one is more on the policy side. Like, for example, since this is an education, right, like that happens because there is no factual ground truth to it, right? Like it's a subjective decision making, and that can introduce observer bias. And later on, we will see how to tackle such a problem at a program level. Finally, model risk governance. So this is a point specific to finance industry, right? So before any model or any machine learning model that goes into deployment, it has to go through independent validation from model risk group. And they test you basically on your conceptual soundness, design choices, assumptions, and the complexity of the solution. So it's a basically very intensive problem process that they do for each model before it goes into deployment. And they try to follow the regulations from SR 11.7. Basically, it's a regulatory requirement to do this governance. So, and what the validation report is can be shared with the regulators as well. Okay. Let's talk about application areas, right? Like once we have understood how the transaction monitoring workflow works, let's understand where all AI can be used, right? So the first one is alert generation. We can actually use machine learning techniques to complement the rules, because right now the rules only generate alerts of known patterns. But if we were to use some techniques like unsupervised learning, we can generate alerts that are not detected by rules and complement it. The second use case would be alert prioritization. So for example, as I mentioned, right, all alerts are treated equally, irrespective of the risk. We can build a model that would rank order the generated alerts for human review. And we can use like a supervised framework, anomaly detection framework for doing this kind of problem. And finally, assist in drafting the suspicious activity report. With the recent advent of LLMs, right, like it's becoming easier to summarize all the analysis, and this is one of the application areas where LLMs could be used. Based on all these three use cases for today's presentation, I'll focus mostly on alert prioritization using supervised learning. However, I'll talk about all the design choices, how do we do the trade-offs while coming up with the supervised learning approach. With that, let me move on to model background, right? Like, so for building a model, right, like we need features and a target variable. The target could be used either to evaluate the model in case of unsupervised learning, or it could be used to learn a function in case of supervised learning approach. With that, I'll move on to observer bias for target variable, because that's also a very important piece that would later impact our evaluation choices, right? So consistency of human review is important for developing the model, right, in our case. And to evaluate this observer bias, we are using a statistic called Cohen-Kappa, right? And high value of this kappa statistic shows high inter-reliability, right? So let's understand like how do we evaluate observer bias, right? Because once an alert goes to one reviewer, they make the decision and then draft the report, right? So there can be some subjectivity. So let us consider two human reviewers A and B. And since it's a categorical variable, whether it's a yes or no, we can create a 2 by 2 grid with all the possible combinations, right? And how Cohen's kappa tries to calculate the inter-rater reliability is basically by calculating a ratio of probability of observed agreement, and then you subtract the probability of expected agreement. Basically, proportion of times where raters actually agree, and then we remove the chances where they would on random choices they would agree on some of the cases, right? So this is basically how you calculate Cohen's kappa, and basically plugging into the formula we can get a Cohen kappa of 0.99. And since it's a subjective grid again, we have a range where we can say between 0.81 to 1, it's almost perfect agreement, right? One thing that I would like to highlight is, right, like since each review takes around like 4 hours to review, right, we cannot compare this observer bias for all the alerts. So we will try to do it on a sample of alerts and try to establish that there is no disagreement, right? Like, and the process of labeling is very objective rather than subjective. Okay. Moving on, now that we have talked about the target variable, right? Let's talk about the data sets, right? Like what kind of features we can use, right? And then we'll talk about what kind of innovative feature engineering we can do to tackle such problems, right? So right now we have two data sets. One is development and one is out of time. And we then split the development data set into train and validation in a ratio of 80-20, right? And out of time vintage has a out of time data set has a different vintage, because this is more like a production data where we want to test like how the model would perform on a completely unseen data set, right? The event rates for both the data sets is around 5%, which is good because it shows that your practices are stable across time. Now, in terms of the features, right, like we can have different typologies of features. We decided to go with some type of features like spend in high risk countries, sensitive industries. For example, sensitive industry could be jewelry or car purchases. Then we can also try to have merchant collusion, whether you are part of some bigger collusion ring or not. The third one is cash equivalent payment. It's a different type of product which is similar to cash, but it involves like cashier's check, bank draft with the amount less than $10,000. But the key distinction is like you try to avoid reporting of this transaction when you're doing this. We also looked at wire payments, like how you are doing payments, geographic information, where you're doing it, ATM related fields, like how frequently are you using ATMs and what the amount is. That is in the transaction related features. Also, previous suspicious activity, right? So for example, an alert was triggered for you, but that was later turned out to be not a suspicious activity. But we can still use that as a signal whether there was previously any suspicious activity for you or not, right? So the model is trained and evaluated using all the historically adjudicated alerts. And since a customer can have multiple alerts for it, right? So we try to first of all, dedupe all the alerts and bring the data to a customer level, because then it becomes easy to score in the production. So that's why all the features for an alert is created at a customer level. And since I mentioned, right, like the features are as of the alert date, because we want to have that view of how the model is looking at the risk when a human reviewer looks at the risk. So this is a quick overview of the datasets. Moving on, right? Like, let's talk about some feature engineering using graph analytics, right? I mean, supervised learning could work pretty well, but there are some assumptions there, right? Like, for example, in traditional modeling, each customer is treated independently, right? Which might not be true in such instances, right? And the features that I talked about previously are only from individual transaction history. So we can use some graph analytics to create some innovative features that have meaningful information, because generally when something suspicious is happening, it happens in rings, right? So for example, I have a graph on the right where I have customer nodes highlighted by light blue and merchant nodes highlighted by light green, right? And they are connected through transactions, right? Like for example, when a customer C1 does a transaction at merchant 1 and merchant 2, they would be connected with a edge. However, if you were to see, right, like this graph would be a bipartite graph, right? And then we can uncover some patterns out of it, right? However, if you were to just look at it, it would still be like traditional modeling. But if you were to capture relationship between entities, right, like we can connect the two customers as well with some common info, right? Like for example, C4 was flagged, but it has a common link with C2. So then that becomes like a bigger node. And there we can start deriving some attributes from this network pattern. Like for example, are you part of some collusion activity or not? So this actually helps in designing the model pretty well. Moving on, as we discussed about the features, what type of features we have, and the innovative feature engineering, let's talk about feature selection, right? Before we actually talk about the design choices. So we followed a three-stage process, right? And it was like we first looked at all the trends of the attributes and dropped those that were contradictory to business logic or domain expertise. So essentially, by trend, I mean we try to create the plot of event rate for an attribute and then see the direction whether it aligns with our logic or not, right? The second one was stability test. We try to evaluate whether there is a data drift between the data sets, between the dev data set and out of time. And any attribute that is unstable at this time would likely cause some issues in the production. So that's why we decided to drop them. And final thing, and I really like this idea, which is random filter. So it is a very simple idea, but very powerful for filtering out attributes. So what you do is you try to add a random feature, which is completely random. So my hypothesis is this random attribute does not have any predictive power whatsoever, right? Then what I do is I train a decision tree on this augmented data set, right? And I calculate feature importances, let's say using some technique like SHAP for all the attributes. And then what I do is I remove all the attributes that have lower importance than this random feature. Essentially saying like you are not even important in a random attribute, so there's no point of keeping such attributes. So this was like a three-stage process that we used for feature selection, and finally we got our final set of features that we could use to design the model. Okay. Okay. So there are two types of populations, right? As I discussed, so the first one is alerted population, and this would be labeled. For example, we would know whether a suspicious activity was filed or not. The second is unalerted population. This is the population that lies below the threshold of the rules, and this is not labeled, right? Now there can be a lot of modeling choices that we can go from here, but let me try to talk about the trade-offs between performance, complexity, and interpretability, right? So if we look at the chart on the right, we have interpretability on the x-axis and the performance on the right, on the y-axis, which goes from low to high, and interpretability also goes from low to high. My ideal zone is I want to have high performance and high interpretability, which is my green highlighted ideal zone, right? And I've also color coded them to add complexity. And this complexity is directly proportional to infrastructure investment that would be required to deploy such models. And that is what the complexity refers here. So if we look at the choices that we considered were GNN, which is graph neural networks, autoencoders, bagging, boosting, isolation forest, and logistic regression, right? What we found was GNN, even though they can give marginal performance lift, they were low on interpretability and high on complexity, which is not a good choice because it's a black box model, right? Because if it offers a low interpretability. And also because of high complexity, it would be very heavy on infrastructure. But since we do not observe substantial lift over our techniques, that is both high in performance and high in interpretability, but it is medium on complexity, we would go with those choices in production, right? So that's in terms of all these techniques, we considered three learning paradigms after discussing about targets and the attributes. So the first one was unsupervised learning, and we chose isolation forest, which is trained on alerted and unalerted population. The hypothesis behind isolation forest is very straightforward. So points that are easy to isolate are anomaly versus points that are difficult to isolate are normal behavior. And that is the core idea behind isolation forest. And the best thing is it does not require any labels for developing the model. We just need the labels for evaluating the performance. The second is like we can frame the problem as an anomaly detection approach or problem, right? And then we can use autoencoders. So how autoencoders works is like it has two parts. One is encoder, one is decoder. So the encoder tries to learn a representation of input in some space, and then the decoder tries to reconstruct the data from that particular space. Again, in the training process, there is no requirement for the labels, right? And since we train it just on the unalerted population, um, the idea is like once you try to reconstruct anomalies or suspicious activities, you would have high reconstruction errors, potentially classifying whether it's suspicious or not. And finally, we can frame this problem as a supervised learning approach. And supervised learning tries to learn a function that maps input to our targets. And we tried using XGBoost using the hybrid approach of having the data and the some analytics using graph, right? But this can only be trained on the alerted population because we need labels. Based on all the design choices and the trade-offs between performance, complexity, and interpretability, we chose XGBoost because it showed the most promising results based on the rank order of the alerts. And that's what our use case is, which is to prioritize the uh, alerts. Okay. Moving on, let's discuss what XGBoost is, right? So XGBoost is a powerful gradient boosting algorithm. And why it is so powerful, right? Because it can handle sparse and missing data. It can capture nonlinear interactions. Also, it is scalable and has fast inference time, right? Which is very important in productionizing in any model. In terms of hyperparameters, so there's a hyperparameter called scale pause weight in XGBoost that can be used to balance the influence of classes, which is very important for our use case. So let's consider that our alerted population is just 1%. And even in that 1% population, I have 5% as my true positives. So overall, in my general population, the event rate is just 5 basis point, which is very low. However, if you were to just use supervised learning approach, as I mentioned, our event rate is at 5%. Also, in terms of hyperparameter tuning, that I'll discuss in slide 18 on how do we actually tune the model so that it's robust and performs well for our use case. Now that we have decided that we'll go with XGBoost, let's talk about missing value treatment, right? Because this domain is very different from others. Missing value actually carries some information in suspicious activity detection. So for example, a rare transaction types appears only in a suspicious activity, right? For example, let's say you are doing some suspicious activity using wire payment. So all other types of attributes would be missing. Therefore, we will always have a very sparse data set for this. That's why we need a very good strategy to handle missing values. Now, there can be 4 big strategies on how to handle it. So the first one is ignore records with missing values. For at least our use case, this is not recommended because missingness has some signal in the data. The second one is imputation. We could use some statistics of the data to impute the values. But again, uh, imputing it would not be very helpful because it would alter with the prediction signal. The third one is we can use some another predictor to impute the values, right? So this is a time consuming process, but it can capture complex patterns, right? And this is a good choice. But there's another choice that has better results, which is based on contribution, right? So for example, in tree-based models like XGBoost, there is a native capability to handle missing values using something called sparsity aware approach. And this is what we found worked the best. And how it works is basically when you are trying to make a split for each decision trees node, what it does is it tries to see whether I want to place a record with missing values to the left or right. So based on the gain in performance, it tries to learn that. And since it's unique to each node, it is learned during the training process. So while testing or while using it in production, you can actually use that kind of information while scoring. So that's why we use this approach, because it directly learns from the data on how to handle missing values. Okay. Now let's look at class imbalance and its treatment, right? As I mentioned, class imbalance for our use case is very high if we were to look at the general population. But if we were to just frame it as a supervised learning, the event rate is 5%, which is still imbalanced. And we need a good strategy to handle with it because of the class imbalance, the models tend to be biased towards majority class, resulting in poor detection or prediction of minority class. And as I discussed, right, like the cost of failures is very high. So we do not want like poor detection or prediction for the minority class, because that's the suspicious activity class, right? So there can be some solutions on how to treat class imbalance, right? So the first one is resampling. So techniques like oversampling the minority class or undersampling the majority class are the best ways to do it. However, the fundamental problem with such approaches is that it alters the distribution of training data, right? And then we need to introduce some kind of weights to resample the data back to the original distribution. And choosing those weights is typically a problem. That's why sampling is not a preferred approach, right? The second one is class weighting, right? Um, and this is more like adjusting the cost function. We can introduce some weights in the cost function for both the classes, and you basically penalize misclassifications of the minority class more heavily than the majority class. And based on how we have framed this problem, class weighting was used while developing the final model, right? And as I mentioned, right, like since this is a ranking problem, we won't use any classification metrics like accuracy or F1 score, because that requires a threshold, which can be subjective. And ranking based metrics are used to evaluate the performances of the model, which will be used in the next slide. Okay. Um, let's discuss hyperparameter tuning, right? Like we have discussed a lot of strategies about how to handle missing values, class imbalance, but now let's look at the architecture of the model, right? Like how do I actually select it? So as previously mentioned, right, like the development data was split in 80-20 ratio into train and validation data sets, right? Let's first talk about the objective, right? Like I want to build a model that is robust enough across the development data sets, which is train and validation and out of time. So how I tune the model is using an objective, custom objective for a use case, which is a rank ordering metric. This could be like AUC ROC or AUC PR, which is like area under the curve of ROC curve or the precision recall curve. And I try to subtract the generalization penalty. And generalization here is the difference between a train and validation datasets. I do not touch any out of time because then there might be some leakage. So the best practice would be to just look at train and validation datasets in terms of the generalization penalty so that our model is robust enough. In terms of tuning, right, like since we can have thousands of combinations and it's very expensive to do evaluation for each uh, combination of hyperparameters, right? We followed a two-phase strategy, right? So the first one was using Bayesian optimization to tune the model. And we performed 100 iterations to select a good choice. Let me talk about the contour plot that we have on the right, because that was used to create and have a more informed selection of the final hyperparameters that would influence the performance, right? So contour plot is basically plotting the loss function based on our hyperparameters on the axis. So let's take an illustration, right, of learning rates versus number of trees, where dark blue and purple means low loss, and bright orange and yellow means a lower loss, right? Sorry, a higher loss. So as we look at the lower left quadrant, right, like where both number of trees and learning rate are less, my loss function increases, right, which is not a good zone to be in. However, if we were to look at the top right zone, which is both increasing the learning rate and number of estimators, right, I would get a better performance. So based on this kind of contour plot, I can select 5 candidates and I can directionally decide where I want to tune the model further, right? And that's where I perform grid search to select the optimal hyperparameters. In terms of the hyperparameters, right, like that we can use to tune for a tree-based models is number of trees, learning rate, max depth, and then we can have a bunch of regularization terms like gamma, alpha, lambda. And again, mean child weight is also a regularization parameter. We also tune to hyperparameters called scale postways. As I mentioned earlier, this is used to influence the loss function during the um, training process. So that's why we actually learned it during the data, instead of setting it to a fixed value. And finally, like a sampling hyperparameter, which is column sample by tree, like how many features do we want to have in each tree while building the model. So this is how we did the hyperparameter tuning. Okay, let's look at model interpretability, right? Since we are working in such a heavily regulated domain, we don't want models that are not interpretable, right? And that's why we went with a hybrid approach compared to a graph neural networks. Interpretability focuses on the understanding of inner workings of model. However, like explainability aims on providing reasons for particular model output, right? Like, so explainability and interpretability are inherently very different. So in terms of interpretability, right, like I want to understand how the model is working. So the first thing would be to evaluate feature importances, right? Like which model is more contributing to the model score, right? So we looked at the top 10 variables, right, at least in the model, just to understand from which typology they come. So for example, the top attributes here are high risk country spend, merchant collusion, and cash equivalent payment. And finally, like we had sensitive industry spend. So these all make sense, right? Like the model is automatically learning from the data which of these type of features can be very uh, influencing on the model score, right? So that's why we see that. uh, the second thing is feature directionality. Once we have looked at the feature importances, right? So in terms of feature directionality, right, I want my model to actually learn the trends that the actual data has. So what we do is we try to evaluate similarity between PDP, which is the partial dependence plot, and the expected trend from actual data. So expected trend, if we look at it, on the x-axis we have the features values, and on the y-axis we have the event rate, basically how the um, scoring should be as the model, as the feature increases, does the risk increase or not, right? However, the PDP plot is more from model derived outputs. So we try to see whether the model is trying to learn what is there in the actual data or not, right? Fortunately for our case, right, like since we followed a very robust um, process of feature selection, we found that all the expected trends aligned with our PDP plots, right? So essentially saying that model is actually learning that is there. However, if there were cases where PDP was of the opposite direction from the expected trend, we would have to review like such cases, because that's very counterintuitive. Because what is there in the data, the model is learning the opposite. Okay. Okay. Moving on. Now that we have discussed about our design choices, how do we do hyperparameter tuning? How do we do model interpretability, right? Now let's look at model evaluation, right? How do we evaluate such a model, and like what are the key considerations we should look at, right? So since I mentioned, right, like this is used for a prioritization use case, we are using ranking based metrics, and we have used AUC ROC, which is the area under the ROC curve. And this basically represents the probability that the model, um, if given, like if we randomly select a positive or a negative sample, it would rank my positive case higher than my negative case. So that's what the intuitive meaning of AUC ROC is. And the second one is decile wise capture rate. So what we can do is we can um, sort the alerts based on decreasing order of probability, right? Like essentially saying the model is saying this is the level of risk, and then we can see like in the top 10 most risky cases, how many events are captured, right? Essentially saying like, if I just were to look at top 10 most risky, 10% risky cases, how many are actually the events, right? So that's why we did that. And in terms of model performance, we evaluated it at both global and market level population. So just to see whether the model is able to learn all the nuances between markets as well as the global population. Okay. I'll talk first about the model performance on global population, right? So on the bottom left, we can see the AUC on validation and out of time datasets, right? So it's quite stable, and we do not observe too much degradation in the AUC values, right? Which is great, right? And in terms of the lift over the baseline models that I mentioned earlier, we saw like it's giving us almost more than 10% lift over algorithms like isolation forest. So which is great for our use case. Now, if you were to look at the decile-wise capture rate, right, which is on the validation and out-of-time datasets, and as I mentioned, we'll create 10 deciles of all the alerts, not just the bad events, right? what we can do is we can assign risk levels to these cases, right? Like for example, deciles 1 to 3 is low risk, 4 to 6 is medium risk, and 7 to 10 is high risk cases, right? So now in the use case we were talking, right? Like for example, an analyst, if they were to see a low risk case, right, they would understand that there's the possibility of those cases turning into a suspicious activity is very low, right? But if they were to look at a high risk cases, right, like which is like the 40% of volume, they now capture more than 98% of the suspicious activity, which is very helpful for the analyst who are actually reviewing the case, right? Because now when they are assigned two alerts, they would know which one to pick first. And I'll talk about one thing later, like how we can also assist them during their review using the model. Okay. Now let's look at the market-wise population, right? Like of the model performance, and this is purely on the out-of-time dataset. So on the x-axis, we have 5 markets which are sorted based on decreasing order of the volume. We have rest of the combined markets and the global performance, right? And we have AUC ROC on the y-axis. A random classifier, and why we chose AUC ROC, because it has a intuitive meaning, right? If you were to randomly classify cases between SAR versus not SAR, it would have 50% AUC ROC. So there is an intuitive meaning to it, right? And 100% is a perfect classifier, right? Like, and it's very difficult to achieve a perfect classifier. And if we observe that across markets also, the performance stays good, right? Like it's above the excellent classifier threshold of 80%, and in some of the markets we observe outstanding performance. So this is how the model performance is on market-wise population. Now let's look at some of the key assumptions and limitations of the model, right? Like, because it's very important to understand whether the model can be applied to some use cases or not, and where it fails, right? So there are two key assumptions while developing such a model, right? The first one is the data distribution is similar in out of time to the data that was used for model development, right? Essentially saying that data drift is not there in the attributes, right? The second thing is that training data was correctly reviewed, right? For example, if I have incorrect labels that we try to remediate through Cohen's kappa, if there were some wrong labels itself, the training process would be hampered, right? And the second thing is manual review criteria is comparable. So for example, the education practices do not drastically differ between when we use alerts to train the model versus in the production, right? Like, so those are some of the key assumptions while developing these kind of models. And finally, the limitations, right? Where it is difficult to apply. So if any new rules or new products are introduced, right, then the model might not be able to classify these alerts properly because the model never saw them during the training process, right? Okay. Okay, moving on to conclusion, right? Like how does the model perform, and like how what are the next steps, right? Like, so for example, it has a very robust and robust predictive performance, right? For example, we saw that it has 94.4% AUC on out of time data set with almost like 10% lift over the baseline models, right? And also it was stable across the two vintages, where we saw that there isn't too much drop in performance across different vintages. The second is efficiency gains, right? Like as I showed in previous slides, almost 60% of the alerts are classified as low to medium risk, right? And because of this classification kind of thing, the investigators can actually prioritize the high risk cases first, because first of all, there is a very high penalty for not able to review it. The second is there is a strict SLA, right? So they can easily prioritize the high risk cases first. And what we found was, like, on average, there was like a 35% reduction in time to review each alert, because they were able to first of all classify which is a high risk alert versus a low risk alert, and they can moderate their efforts for each kind of alert. And the third point is AI assisted investigation, right? Like, for example, we can use some techniques like SHAP, uh, feature attribution, so that we can provide some top contributing factors for each alert to our investigators, right? So they can then use that as some starting point for their review instead of starting from square one, right? Like, so basically they have some informed direction where they want to actually look at the alert from, right? And it's a scalable framework, right? Because it provides a compliant pathway for financial institutions to transition from rigid rule-based systems to risk-based and intelligent monitoring, right? Because the thing is, the model is designed as such that um, it not only classifies the alerts into low, medium, high, it also provides uh, interpretability. So this is an effort to a white box model rather than using just a black box model, which is very much required for a heavily regulated environment. Okay. With that, I would conclude my presentation and thank you.
Thank you, Parth, for your excellent presentation. Now let's move to the Q&A session. I think there's one question from the chat. Let me read the question first. Can the actors involved in the money laundering be grouped or clustered? Would the different model parameters be appropriate for different groups? What if there is a new actor who doesn't fall into these groups?
I mean, that's a great question, right? Like, and that goes on to show the limitations of model, and that's why we have human in the loop kind of thing, right? Like, because these models are designed to assist the review rather than like do the review itself. So for example, if we have some factors that were not part of it, the during the review process, the analyst would look at such activities. But I agree, right? Like, the risk could be slightly misclassified, but it still goes through a human reviewer who would actually look at the case in its entirety.
Thank you. There's another question from the chat. Are there any open datasets available for this type of problem?
I will have to check, but right now I'm not sure if there are open datasets.
Okay, so in your research, you used the internal dataset from the bank.
Right.
Okay. Any other questions? Probably I have one question I want to ask because of your talk is very interesting, particularly very important in the bank and real world applications. So I would like to know, because in your methods, you mainly using the ChatGPT boost algorithm, right? The machine learning algorithm.
So could you repeat?
You are using the boosting method for
Right.
your applications. But now the deep learning methods are very popular in prediction or classification. So would this also be a trend in these applications?
Sure. Let me go to one slide, Professor Ying, that would classify this, right? So at the end, it's all about trade-off between performance, complexity, and interpretability, right? Like,
Yeah.
so if at least what we found was like neural networks in a tabular setting are still not able to give a substantial lift. And I have a reason for that, right? Because um, neural networks, right, like they try to uncover patterns, right? But in a tabular data setting, you already have attributes and you have some kind of assumptions that your rows are independent and features are also independent, right? So that's where neural networks are still not able to like outperform the traditional methods in a tabular data setting. However, they are still great at uncovering patterns or how there can be some dependencies in the backend. So they are mostly good at uncovering patterns. So for example, I'll give you image data set, right? Like image has some kind of dependency. For example, a pixel is related to the neighbors, right? So there is some spatial structure to it, and that's why deep learning techniques work well. But in a tabular data set settings, it does not work very well. And I think there were recent papers as well that shows, and I think it's called deep learning is not all you need for tabular data set. So it's
Yeah,
so
I
there,
really like your
there is
point on the interpretability. This is also very important.
right.
So there's another question. Thanks for the quality of the presentation. In the feature selection processing step, how to know which model or statistics test has to choose? Have to choose.
So so
In
in
the
which
chat. Yeah.
right? So in which stage are we referring to? Which statistic? Like as in, if you could clarify, like which statistics are we referring to?
Okay. And also, Duga asked how to access presentation slides. I think probably you can learn for your spot. That's all from me. Thank you. And we have webinar on 12th of May. And Tom also shared the link in the chat. If you are interested, you can also do the registration for the next CIS webinar. Thank you.
Thank you, everyone.
Thank you.